Hello, this is Monday's class. How are y'all doing? I hope you're doing fine. Hope you had a good weekend. I had a good weekend. We're talking about value of statistical life. Today, to motivate this, let's think about what would happen if we did not try to value lives saved in environmental policy. And the reason for this thought exercise is because some people do not like the topic and don't like the moral or ethical implications of valuing people's lives. So here's a paper from 1996 that looked at regulations that were approved and regulations that weren't approved. And from those decisions, tried to develop an implicit value that policymakers were placing on life saved. So here's the data that Van Houten and Cropper used. Here is the policy was banning products that used asbestos. Oops, sorry. And here's the products that used asbestos. And here's the cost of banning the product. And this is in millions of $1989. And then the third column is the number of cancer cases avoided by banning the product. And the last column is the cost per cancer case avoided. So the cancer cases avoided divided by the cost gives us this number in millions. So for drum brake linings, the cost of the product ban was about $14 million, but it saved 136 lives. So the cost per cancer case avoided was only $100,000. That looks like a good product to ban. Okay, the cost was not very high. And you can see this is ordered from the lowest cost per cancer case avoided to the highest. So for automatic transitions components, the total cost of banning that product was only $200,000. Okay, it saved less than one life. Okay, this looks like it's like 4 out of 10,000 people were exposed to 4 out of 10,000 in risk. But the cancer case avoided, the cost per cancer case avoided, was pretty high. Okay, so this product was banned. Okay, it had a very low benefit and a high cost per cancer case. So you can see between these, within this range, there's a lot of variation. Now compare that to the products that were not banned. These products were allowed to be bought and sold with asbestos in there. And the cost per cancer case avoided varied from 43 to over 11 million. So it looks like some of these high cost per cancer case avoided calculations, it looks like maybe we should not, maybe those were good decisions. But for some of these others that had a relatively low cost per cancer case avoided, it looks like these numbers are similar to some of the numbers for the products that were banned. So the point of looking at these numbers is that some of these decisions appear to be fairly arbitrary. And if this calculation was made, okay, which it was not, this calculation, the third column, was made by the authors. If it was made by the decision makers, they could have made a more informed decision about whether the product should be banned or not. So that's what we're trying to do with the VSL. We're trying to come up with a standard way of estimating the per unit benefit of environmental policies in terms of life savings. Okay, and that's where this table ends up coming from that we've seen before. This is the VSL estimates, value statistical life estimates used by the US EPA for a long time. Okay, the numbers range from 0.85 to about $20 million, and this is in 2006 dollars. Okay, and we have played around with these in class and come up with an average of these, which is basically what the US EPA uses. These are based on labor market studies and contingent valuation studies. And we'll talk about where they come up with those numbers. Okay, so that's why we do this and what the VSL numbers look like. So let's talk about how those things, how economists develop those VSL numbers. Okay, the idea is that values of statistical life are based on people's decisions that we make every day. If you ever hear someone, you describe a situation that you're in, and someone says, well, you just took your life in your hands. Well, you just made a risky decision. That means you made a risky decision, and in doing so, you compared the private personal benefits of the decision with the private personal cost, and you decided that it was a good thing to do. Okay, on the other hand, sometimes there's decisions that you make where you do not pursue the risky behavior, and that's because you think the costs are greater than the benefits. So people make decisions like that all the time, and what economists try to do is analyze those decisions and try to see if we can develop estimates of this VSL. Okay, so the VSL is based on the values. These are the amount of money that individuals trade for small changes in their own probabilities of living. Okay, so for example, if you pay more money for a house that is located farther away from a Superfund site, then in return, you get a reduction in exposure to a toxic substance and a reduction in your risk of dying. And so the individual homeowner is willing to pay more money to avoid risk. Okay, if you buy a product that reduces your risk. Okay, then, for example, if you buy a basement ventilation system, then you get a reduction in risk of exposure to radon. And in the labor market, if you work for lower pay at a job that has less risk, then you are revealing your preferences for less risk and the amount of money that you would be willing to trade for that lower risk. And as an example of this, I don't know if the TV show is still on, but what was it called? It was about the oh gosh, I'm gonna pause. Okay, I'm back. I googled. There we go. Deadliest Catch. So those crabbers are paid a lot of money. I think they're crabbers up in Alaska that pay a lot of money, but it's a very risky job. And so the wage premium reflects people's willingness to accept the higher risk of death for more money. And coal miners have the same thing going on. They're paid relatively high wages for their skills and abilities, and they're part of that high pay is a compensation for the risk of death. Okay, so once you have data like that, once you've come up with information, there is a certain way that the numbers are compared. So imagine that the wage premium or the price that you pay for the product that reduces your risk, or the higher price that you pay for the house that's further away from the toxic site, call that your willingness to pay. If you divide that by the change in the risk that you're buying, then that gives us an estimate of the VSL. Okay. Okay, and this unit change. Okay, so we're really not estimating the value of a life saved. We're estimating the willingness to pay for a small change in the risk of death. But this is what is called a value of statistical life. Okay, so think about this. Suppose there's a group of 1 million people, and that we know from epidemiology studies and other things that 8 of those people on average will die every year due to exposure to some pollutant. It could be air quality, it could be a toxic release. Okay, but the identities of the people who are going to die, we don't know who they are. So these are anonymous people. We never can attach a name to or face to VSL. Okay, now consider an environmental policy that will reduce the number of deaths to 7. Okay. Then the change in mortality risk, delta R, is equal to 1 divided by 1 million, which is .00001. Okay, now there's nothing special about a policy that changes death from 8 to 7. This could be a change from 8 to 4. And if that's the case, then this number in the numerator would be 4 in a million. And then this number would be, that would be 4. Is that right? All right, let me pause again, make sure. All right, I thought that might be wrong. Risk of a change of 4 in a million is 0.0000 with another 0 and a 4. Okay. Okay, so then, if each person is willing to pay $9 for the policy, or any number, I'm just pulling a number 9 out of the air, not out of the air, but you'll see why I'm using 9. The value of the unknown statistical life saved is the number of individuals times the amount per individual, or 9 million. Okay, now that's one way to calculate it. Okay, 9 million equals $9 to save one life times a million people exposed. The other way to calculate it is by taking the $9 and dividing that by the change in the risk, and that'll give you 9 million as well. So both of those are equivalent ways of calculating the VSL. Okay, in terms of methods, we've talked about these labor market studies, and these are just like hedonic housing price studies. These are called hedonic labor market studies. So imagine if you're willing to forego an extra $30,500 per year to increase the probability that you won't have a fatal on-the-job accident by 1 in 1,000, then you would value your life at $3.5 million. And I say or more over here because this is a lower bound on that value. That's a technical issue that we probably won't talk about. So the $3,500, that is a lower annual salary. Okay, an averting behavior study. This is when we use product market purchases, and the products are things that keep us safe, like seatbelts. Okay, and it used to be in the old days that seatbelts were an extra feature in a car, and they had a price attached to them. And so economists could look at purchases of cars with seatbelts and compare the change in the risk of dying with seatbelts and without seatbelts, and in that way estimate a VSL of something like 3 million. Okay, and there are contingent valuation studies in the EPA's list, and what you do there is just directly ask survey respondents for their willingness to pay for a reduction in their fate or their own fatality, or their a small reduction in mortality risk for anonymous people. The data that we're going to look at is contingent valuation, where we're looking at people's own fatality. Okay, so let's just review the evidence here. Here's a paper in the Journal of Risk and Uncertainty, published in 2003, The Value of Statistical Life, a critical review of market estimates throughout the world, written by Kip Viscusi, who is one of the, maybe the leading scholar in hedonic wage risk studies. His co-author is Joe Aldi. So here's a table of estimates, and these you can see where you can see the research study. Okay, and here's the data set. The PSID, that's a labor market study. I forget the panel study of income dynamics. CPS is a current population survey. Okay, and these authors did their own survey. QES, I'm not sure what that is, but these are all big labor studies, or data sets that contain people's incomes and their job characteristics. And so then you include risk variables estimated from different sources, and you might just take the occupation, find out how many people died on the job over the course of the year, find out how many people worked on that job, and that ratio is the risk of death in that job. So here's the mean, the average risk used in the study. This is a qualitative variable. If risk of just being hurt, non-fatal risk, are included in the study, whether workers' comp is included, the average income level, and here's the VSL implied from the data. So 700,000, 2.1 million, between 7.1 and 15 million, between 9 and 11. Okay, so you can see that these estimates are, there's a pretty wide range of those. Okay, here's another study written by Glenn Bloomquist, who was my dissertation advisor at the University of Kentucky. And early in his career, he did a lot of these averting behavior studies. So he wrote this review of the literature under contract with the Environmental Protection Agency, and they used it to do sensitivity analysis, consider sensitivity analyses relative to their list of 26 labor market and contingent evaluation studies. Okay, so here are the types of behaviors that are in the averting behavior literature. Speeding on the road, bicycle helmet use, car seatbelt use. There's one of Glenn's studies from the 90s. Child safety seat use, trying to estimate the value of children's lives. There's 3 with car prices and safety features included. And here's a hedonic analysis of housing prices. So Glenn included a hedonic price model in with the averting behavior studies. Okay, just like with the labor market, here are the estimates, and sometimes there's a range of estimates, 2.8 to 4.6 million. And you can see that there's a less of a wide range with these studies than there is with the labor market studies. Okay, and then Kochi, Hubble, and Kramer did an analysis of labor market and contingent valuation estimates of the value of statistical life, and this is their statistical distribution of those studies. So here's the contingent valuation probability density function. On the horizontal axis, we have the value of statistical life. You can see that it's centered below 5. I think that's like 3.5 million. I forgot to mention something with Glenn's study. His best estimate. The simple average value he calls his best estimate. That's 4.5 million. Okay. And then there's some other variations on this, but keep the 4.5 million in mind. Okay, so the contingent valuation study is about 3.5 million is the average. And you can see there's a pretty wide distribution. Hedonic wage studies, the average is about 9 million, and that's where I'm using that's why I grabbed the number 9 earlier on in my little number example. You can see that the range of the hedonic wage studies goes from 0 to 25 million. There's a 25 million study out there. It's a low probability because it's only one. So most of the probability density is centered around between 5 and, let's see, 5 and about $12 million. Okay, so the question then is, well, should we be using contingent valuation or hedonic wage studies? So here's a review of the literature by Viscusi in the Journal of Economic Surveys. And he says that one finding he has is that the results from revealed preference studies, that's hedonic wage studies, are systematically higher than those from stated preference studies, potentially limiting the usefulness of stated preference studies in generalizing the VSL estimates to different populations and kinds of risk. So he says there's a systematic underestimation of lives saved from stated preference studies, like contingent evaluation. And it's going to be difficult, therefore, to use those stated preference studies to think about older people or younger people and different types of risk. Okay. Now, he says that, and that's highly influential for labor markets, for VSL studies used in the United States for policy purposes. The EPA and the National Highway Transportation Safety Administration, a couple other federal agencies, all seem to rely on these reveal preference studies, these labor market studies, and they use a number that's about 9 million these days. Okay. In contrast, in Europe, so the Europeans are more likely to use stated preference studies. This is a screenshot from a web page from the OECD. Okay, this is they talk about their meta-analysis of VSL estimates. So think about let's look at the second paragraph here. Environmental pollution, for example, typically affects the youngest or the oldest part of the population. Okay, the most, and then we have a typo here, the most, parenthetical, closing parenthetical, and mortality results. So I think the and shouldn't be here. The most mortality results from long-term pollution exposure and exacerbation of pre-existing medical conditions. Okay, so they're saying that most of the lives saved by reduction in environmental pollution are for old people and young people, and these are not accidents. It's more exposure to risk and trying to avoid that. And they're saying that hedonic wage studies are based mostly on male workers in their prime years that have accidental deaths in the workplace. So they're saying that that $9 million probably doesn't apply to older or younger people who are having to deal with environmental pollution. So, therefore, a growing body of research uses stated preference methods instead. For example, contingent evaluation. And then they describe what a study like that is all about. Okay, so this is you click on this, you can get a book. There's another link down here where you can click on the Excel spreadsheet with all the studies that they used. Their number is... the number that they use, let's see if I can find it here in my teaching and benefit cost analysis book. Goodness, where did I find it? There it is. The OECD recommends that the VSL range should be 1.5 to 4.5 million. With a base estimate of 3 million, okay, which is closer to the averting behavior estimates that Glenn Bloomquist developed. So I'm always inclined to go with those lower estimates for the reasons described by the OECD. I'm more skeptical of this $9 million figure. And that's just my opinion. Okay, so let's try to figure out how to estimate this. So here's a paper that I helped out on with Glenn and Patty Ryan. This is her dissertation back in the early 2000s. They presented this at the American Society of Health Economists back in 2010. Okay, so with they did 2 surveys, and the second one is a treatment survey where they listed the willingness to pay for a procedure that could lower an individual's risk of heart attack by treating vulnerable plaque if it's found. So this is vulnerable plaque is what's caused by cholesterol. So this is a hypothetical procedure that would also provide better information on the actual risk of heart attack to the patient. So they surveyed 211 adults who had already been diagnosed with heart problems and who answered 5 CVM questions. So here's what the data looks like. Okay, this is the percentage yes that the person would buy the medical treatment by the bid amount, or the price of the medical treatment. Along the top is the price, so its cost range from $1,000 to $10,000. And in the first willingness to pay question, which is the data that we're going to look at, you can see that if the price was $1,000, these people were 90%. 90% of these people would buy the product. As the price rose, the percentage of people who would buy the product falls, as economic theory suggests. And when we get up to $10,000 price, 37% of the sample would buy the product. Okay, and the data also includes an estimate of the risk change. So survey respondents were presented with a line that depicted the annual risk of fatality per 10,000 people. So for an auto accident, 19 out of 100,000 people die annually. That's the risk that we all face when we go out and drive, on average. Safer drivers have a lower risk, riskier drivers have a higher risk. So there's heterogeneity in this number, but this is the average. And then they said that the number 50 out of 100,000 is defined as high risk. So then people were asked to rate their own risk of having a heart attack within the next year using this scale. And so 0 to 50 was described, and then survey respondents were asked to enter the number that best describes the risk of having a heart attack in the next year. Okay. So each person was described the treatment, and they entered in their own risk of having a heart attack, and for our purposes, we'll just assume that that's a fatal heart attack. And then they're asked, now that you've considered all of these things, if this treatment cost bid, and each person was randomly assigned one of those bids, 1,000, 2,000, up to 10,000, would you choose to have the treatment done? And they would say yes or no. Okay. Okay, so up on As You Learn are these data in SPSS format. There's 4 variables in the data set. The variable yes is equal to 1 if the person is willing to pay the bid amount, and it's equal to 0 otherwise. And the bid variable, that is the cost of treatment, that's the 1,000 to 10,000. Each person got one of those costs. The risk variable is their own perceived risk of death, and that should be 100,000. I labeled that with missing a 0. Perceived risk of death in 100,000. And then DR is the change in risk of death as a result of the treatment. So we're assuming that if you buy the treatment, then your risk of death goes down to 0. And so DR is equal to risk divided by 10,000. And here's the descriptive statistics for the sample. Here's the yes variable. So 64% are going to purchase the treatment. The cost of treatment ranged from 1,000 to 10,000. The average is 5,583. The perceived risk of death in 100,000 ranged from 0 to 100. Some poor person saw that high risk and said, yeah, I've got double the high risk, so I have a risk of death of 100 in 100,000. So the average of that is 30.5. And then the change in risk of death as a result of the treatment is 0.003. And let me make sure I've got the correct numbers in there. So 30.5 divided by 10, 100, 100,000 equals 0.0000305. So I'm going to change these two things. I'm going to fix this SPSS data before I load it up on as you learn for you. So there'll be an extra 0 in there, and there'll be an extra 0 right there, so that the risk of death should look like that, 0.00305. All right. So your job is to estimate two contingent valuation method VSLs. First, you estimate the VSL with the turnbull, just like we did in class on Monday. So with that data, click on Analyze, Descriptive Statistics, and crosstabs. And you'll get percentages, percentage yes at each price. Graph that out in that step function like we talked about. And I think the notes are posted for that. And all right, I took a call. So check out your notes from Monday, see how to estimate that. And then estimate the probability curve with OLS regression. And in SPSS, click on Analyze, Regression, and then Linear. And you should estimate a straight line, graph that thing, calculate the area of the triangle, and that's your willingness to pay estimate. Okay, and then with those two estimates, just estimate VSL equal to the willingness to pay divided by the change in the risk. Okay, I want you to submit a PDF of your SPSS analysis. So to do that, click on File and Print. And here you see there's my output in the background. Print to PDF. And then there will be a screen on As You Learn or an upload button where you can upload your PDF. And then I will send out I'll post a SurveyMonkey survey on As You Learn where you can input your two VSL estimates from your analysis. Okay, so that's the assignment for Monday. This will be posted I'll send out an email when it's posted, and you will have received that email before I told you that. So that was just a stupid thing to say. But I'm not going to edit it out. So enjoy class on Monday. If you have any questions or comments, send me an email. And have a happy Thanksgiving. And I'll see you back in class on Monday.